when we talk about how geometry connects to the mining method, the link is very direct. A narrow step vein almost always pushes you towards mechanized cut and fill or narrow long hole stoping where angle tolerances are tight and the optimization must produce stopes that follow the vein without violating minimum mining widths. A gently dipping stratiform deposit naturally leads to Roman pillar and its variations. So you start with a grid of rooms and only afterward decide which cells are profitable for the first phase. A massive ore body with typical wrong strength usually points to sublevel stoping or similar methods where large stopes are acceptable and the optimizer can smooth the outline to reduce the number of separate extractions. And again, this all comes back to geometry. If we don't look in the ore body type and the allowed orientations at the geometric stage, we'll end up optimizing shapes that the designer will later have to slice apart anyway to make them fit the chosen mining method. Another important constraint at this stage is accessibility and routability. In underground mining, there is no point optimizing stopes in areas that can't actually be reached with an acceptable gradient, turning radius, and ventilation pathway. That's why we typically add an access graph to the geometric model representing levels, blind drifts, raises, and ventilation crosscuts. With that in place, we can introduce a direct constraint like reachable stope, which is true in the optimization, ensuring that all subsequent IP/MIP models consider only those geometries that are truly accessible from the existing infrastructure. In the simplest implementation, this is just a binary reachability matrix between graph nodes and stope centers. And in more advanced setups, it becomes a development cost function for providing access, which can then fit directly into economic evaluation. And it's only after all this, after aligning clusters with ore body, applying geometrical trimming, running the MCDM ranking, and confirming that each stope is actually reachable, that it makes sense to move on to the economic calculations in any linear or integer optimization models. By that stage, we are no longer dealing with idealized polygons from the block model. We're working with stopes that can truly be blasted, ventilated, and backfilled. This is exactly why geometry comes first. It defines a realistic search space for everything that follows and filters out the solutions that might look great mathematically, but will never survive in a real mine.